Okay, still we discussing about chapter 15, which is a bulk metal deformation process. And as you know, chapter 15 is a 4 item: rolling, foraging, extrusion, wire and bar drawing. Already rolling finished, rolling already finished, foraging already finished. Today we'll talk today about the extrusion. This is the third item that we're going to talk about. So today we're going to start the extrusion, the third process in a bulk metal deformation. Remaining is a wire and bar drawing after that, right? Extrusion. Extrusion, as you can see, is apply pressure. I already started this one before, but just to quickly refresh your information, I remind you. Uh, we apply pressure, we push the material to exit with the same shape of the die exit. You can see here, this is a raw material, it's cylindrical shape, usually cylindrical shape. We put here, we apply pressure, right? Can you see that? We apply pressure, we push here, we apply pressure, we push the material will exit exactly as the same shape of the die. So die exit like this, then exit same shape of the die exit. That's what we call extrusion, mainly pressure. Mainly pressures. We apply pressure, material will exit with the same die opening shape, right? This is the extrusion process. So as I told you, same as I told you, so material here, it is initially cylindrical shape. We put the material, we apply pressure. When we apply pressure, material you see that will exit exactly with this is a die opening shape. This is a die opening shape, so material will exit exactly like the die opening shape, same like die opening shape, right? Volume is constant. Volume is constant. Starting volume equal to the final volume. So then you can see that cross section will dimension cross section. I mean the cross section dimension will change, right? Then length will be also different. So length will be also different. Let me show you something. Just give me a second. Let me show you a nice video to describe the extrusion process. It's coming. Yep, right. So here, let me start again. This is the extrusion process, the extrusion machine. This is a pellet, is a raw material. We put in a furnace to make it soft, a little bit soft. Maybe warm, or maybe cold, maybe sometime hot. It depends on the dimension. This is in the furnace. It's become hot enough, become soft. This is the part that we're going to extrude. This is the raw material. This is the raw material that this is some oiling. We put some oil to facilitate the motion. We put here, and then this is the pressure. We apply pressure. You see that it will be long, very long. Why? Because the dimension change, cross section dimension see become very long, and then cut again one more time. Again one more time. This is a pellet. We put oil here. Then you put in a machine. This is a hydraulic system. They apply pressure. You see, it is small in length, but the length here, you see, is much, much longer because cross section, the volume is constant, guys. Volume is constant. Right here, we cut as the dimension, needed dimension. Another one is coming here. There's another one here. This is the extrusion. You see, it is long, 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 long distance. Here, this is the extruded part. Here, probably we cut with the required dimension, exactly as the needed dimension of the extrusion. Right, so this is the extrusion process. Right. So this is the extrusion. This is the extrusion process, as I told you. Then we put the material inside here. We put the material inside here. Then you apply pressure. Whenever you apply pressure, material will exit. Exactly. So you see, this is a die opening shape. Then material will exit with the same shape as the die opening. It is a cylindrical. Initially, it is cylindrical shape, right? But what about exit? It will be, is this one short? You see, it's not very long. It's short, but this one will become very long. So it is the extrusion process. In extrusion process, we have two types of the extrusion. Two types of the extrusion. Right? The first type of extrusion, we call it is a direct extrusion. Please listen to me carefully. Direct extrusion. This is a direct extrusion actually. You put the pellet here. This is a pellet. It is initially cylindrical shape, as I told you. We put it inside. We apply pressure. Material will exit from the other side. The direct extrusion, you can know that the pressure in the same direction with the material flow. So you apply pressure in this direction, material flow in the same direction. Right? This is very important. You apply pressure in this direction, material will flow in same direction. This we call it is a direct extrusion. Right, so direct extrusion, pellet move in the same direction, as you can see. However, there are a friction in the wall here. Whenever you apply pressure, this is very difficult process. Whenever you apply pressure, material will not easily to flow in this direction. So it will flow axially and laterally also. Material will flow in this direction also as well, but cylinder is there, will not allow material to flow in lateral direction or radial direction. Then material here will not expand because the cylinder here, but the friction here will be high. There will be high friction between the wall because you push the material need to move, then will be high friction here in the wall. This is the direct extrusion. Then friction here increase the ram pressure. Friction increase, this is the ram pressure. Friction here, because ram now not only you apply pressure to flow the material, yes, it is to flow and overcome a friction in the wall also in a direct extrusion, right? Next is the indirect extrusion. We call it is a backward extrusion and we call it is a reverse extrusion. Same meaning. So what is the feature of indirect extrusion? The feature of indirect extrusion, can you see here? The feature of indirect extrusion is that this is the ram. Ram is hollow. Ram here, this is the ram. Can you see that? This is the ram. Ram is hollow, not solid. Then when you apply pressure, material will not exit from the other side. Material will exit inside the ram, will flow inside. So you push like this, material will flow in the opposite direction. Opposite direction. Then whenever you apply pressure, material flow in opposite direction. This is whatever we call indirect extrusion. This is the difference between direct extrusion and indirect extrusion. So material flow in opposite direction. In this case, no friction in a wall. No friction in the wall because material here, no relative motion between the material and wall, right? So no friction in the wall. This is a benefit. I mean, indirect extrusion is better off compared with the direct extrusion from the point of view that there are no friction in the wall. However, in indirect extrusion ram is weak. Ram is weak because it is hollow. So it is weaker than case of direct extrusion. In direct extrusion, ram is more harder, more stronger. Huh? So lower extrusion force is required here relative to the one in case of the direct extrusion. This is a big difference between direct extrusion and indirect extrusion. For improvement, there are whatever we call is the hydrostatic extrusion. Hydrostatic extrusion is direct extrusion. Hydrostatic extrusion is a kind of direct extrusion. So what is the difference between a hydrostatic and direct? The only difference here, we fill the gap here. Can you see that? We fill the gap here with a liquid oil, hydraulic oil. So we fill a gap here inside with a hydraulic oil. Then when you apply, there are no direct pressure between ram and workpiece. There are no direct pressure between ram and workpiece, but the pressure will transfer through the oil here. This oil surrounding. This oil, as you can see here, surrounds. When you apply pressure, pressure will transmit through the oil to the workpiece. Then apply pressure in all direction, and then material will flow, as you can see here. So this one helps. This one improves. There are no friction in the wall. Pressure will be less. homogeneous, isotropic, mean the deformation in all direction. It's perfect actually. It's very good improvement or very good modification. However, the biggest problem here is the sealing, because the oil will like to escape. Then sealing an issue here. Sealing an issue. Brittle material here can be extrusion or extruded by this kind of hydrostatic, but sealing is a problem. This is the biggest problem in this one. Okay, extrusion with a mandrel. Extrusion with a mandrel being used to create a hollow shape. And you see that extrusion with a mandrel is to create a hollow cross section, not solid, but hollow cross section. This usually done, this is a raw material. We create a hole in raw material. Initially, the raw material must have a hole. Then this is a mandrel. We put mandrel and we apply pressure. We put a mandrel inside. This is a mandrel and we apply pressure. Material will exit around here between the mandrel and the wall. There are a gap between the mandrel and the die opening. Material will flow here to exit in this dimension. Then you can just create whatever we call is a hollow cross section. This is the extrusion with the mandrel. Extrusion with a spider. It is exactly similar to extrusion with a mandrel, but instead of putting mandrel, we put a spider. This part is a mandrel. This part is a mandrel here. This one we replace with this one, and we fix here. Instead of it is moving, we fix here. So it is a spider. We call it spider leg. So spider leg here, we put spider leg here and mandrel inside to fix the mandrel in this position. So this is a mandrel. This is a photo actually. This is a mandrel and this is a spider leg, right? Spider means the leg of this leg to fix mandrel inside. Then material, when you apply pressure, material will flow around to exit from this one, and then will stick later. It is hot. Then when exit will stick, combine each other and combine each other later to create a solid, and then hollow cross section. This is a hollow. So material, you see, material exit to create a hollow cross section. This one we call is a spider. Different type of a spider to create different type of shape, different type cross section. Then different cross section can be produced. This one, this one, this one, this one. Different shape can be produced from the extrusion. Right. Next is whatever we have is a cold extrusion. Cold extrusion, as you can see, it is a process carried out in room temperature or a little bit high, few hundred degree, but less than 0.3 melting temperature. And this one to produce whatever we call is a cylinder. This is a hollow cylinder. This is a ram. This is a ram initially like this. The ram will come, this initial workpiece. This is a part that you would like to produce, and ram will come, will impact the workpiece, will apply pressure on the workpiece. Here will flow material. Here is an apply pressure. Material will flow around. Material will flow around here. Can you see that? To create a hollow cylinder. Increase the strength and strain hardening, high round force, close tolerance, improve surface quality, no oxide because this is cold working, and high production rate. Let me show you, because still I believe you don't imagine this one. This is a production, is a hollow cylinder. Initially, you start with this raw material and finally you get this one. I believe you don't imagine this one. Let me show you, try to show you something related to this. Let me just give me a second. Yep. Okay. Right. This is cold extrusion. It is not very clear. He will come closer. He will come closer. This is a machine. You see, he put here the workpiece. It is cylindrical, small part is a plate. This is a workpiece actually. He put it. Machine is here. He will come closer. Not clear. I don't see whether I realize or not. Material is, you see, it is moved up here. Here, this is a part. Now it's getting closer. You see the material? Can you see that? Is it clear? This is a part here. This is a raw material. Can you see? It is a plate. Then you put pressure, apply pressure, material flow up. Material flow up. This is a part. This is a hollow cylinder. So initially like this, yeah, but it's cold working as you can see, or a little bit heated. I mean, few hundred temperature. I mean, less than 1 melting. Then you apply pressure here. Material flow up here, as you can see. Between the gap, in a gap between the let me go back to slide. So you can see again, then you see that this is a plate, initial plate we use, right, in a cold extrusion. This is a ram, right, we put here, and this ram, when ram apply pressure, material will flow up. Material will flow up here, will flow up in a gap between the ram and the diameter, the die diameter. Then material will flow up to create this kind of hollow cylindrical shape, which is initially like this. Initially like this, finally you get this is a in actually this one is indirect extrusion, backward extrusion, right? Next is the impact extrusion. It is exactly same. Exactly same. The only difference between impact extrusion and the cold extrusion is that the impact extrusion is performed at a higher speed. Impact extrusion performed at a higher speed and shorter stroke. Higher speed, higher ram speed, and shorter stroke to reduce or to produce a shorter part or produce shorter production. Right? This is whatever we call it is the impact. That's why we call impact extrusion, because it is a higher speed, right? Next is the hot extrusion. Hot extrusion mean if we can or if we apply heat and heating the palette of the material, heating the palette of the material. We call it is a hot extrusion. Why we do this one? Sometimes we would like to extrude whatever we call brittle material. Brittle material very difficult to extrude, or hard material, very hard material, very brittle material. This kind of material, which is a very hard material, very brittle material, is very difficult to be extruded, right? Then it's better to heat it. When heated, it can be extruded. Then we call it is a hot extrusion. However, this is very good, excellent. Actually, this is no way. If you're going to extrude a hot material, I mean a hard material and brittle material, no way. You must heat it. You must heat it. So we call it is a hot extrusion, right? However, in case of the hot extrusion, what is the problem with the hot extrusion? Those should be very fine. Okay, it's excellent. But the problem is with the hot extrusion, when you're heating the material becomes soft. Friction increase. High friction is introduced, as we described earlier. In this case, lubrication is needed. In this case, lubrication is needed here in a wall actually, and here. In this case, lubrication is needed, and they use whatever we call glass powder. Glass powder lubrication being used to facilitate the motion and easily produce this kind of process. However, this process definitely cost is expensive and maintenance is high, but some cases, no way. Some cases, no way. We must have the hot extrusion. We cannot just do extrusion unless we heat up the workpiece material, right? Okay, then this one leading us to talk about friction. This one leading us to talk about friction. This is initially material like this. When you put here, when you apply pressure, there are a friction here, friction in the wall here. This friction in the wall, can you see that? This friction in the wall non-homogeneously flows the material. Non-homogeneously flows the material, as you can see. then material will flow. Then this is a pattern. This is a pattern, material flow, because you would like to come from the big dimension to small dimension to move up a material non-homogeneously deform, and then this is usually the pattern of material to flow in the extrusion process due to friction in the wall, right? For if you talk about the homogeneous case, no friction. Ideally, if you just imagine no friction is something like this. But whenever you have a non-homogeneous deformation, whenever you have a friction in the extrusion process, whatever we call here dead zone will be created. This is whatever we call dead zone. Dead zone, it means this area will never flow, because material will flow in this kind of pattern. Material will flow in this kind of pattern. Dead zone here will never flow, will not be able to flow, because the friction definitely is a friction. Whenever friction increase the dead zone, can you see that? Dead zone is small, dead zone is bigger here. For sure, we need to lubricate here. In general case, we need to lubricate, whether you talk about cold working or hot working or warm working. In all cases, you need to lubricate to reduce the effect of the dead zone here, because here friction is significantly affecting the process. So you need to lubricate to reduce, and many several defect also produce if you not do proper lubrication, and so on. Many defect happen. I will discuss about the defect at the end of this process. This is the extrusion. Let me talk about the analysis of extrusion. This is the extrusion. This is the material, raw material. You put the raw material here. You apply pressure. You apply pressure. Material will flow, exit from the die opening here with the same dimension of the die. We have AO. AO is the initial area. We have AO is the initial area. AF is the final area. So you start with initial area, you end with the final area. B is the pressure applied. LO is the initial length of the workpiece, cylindrical workpiece material. LF, a final length of the extruded part. L is the remaining length, and is variable. LO is constant, initial length before we do. LF is the final length after you complete the process. L is the length during the process. L is the length during the process, or remaining length during the process. Whenever I apply pressure, L is reducing here. L is getting smaller, 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 and finally, the part finish, all part will be extruded. Alpha is the die angle. Here, this is the alpha, is the die angle. Pressure here, and here extrusion force. This is the pressure. Extrusion force equal to what? Equal to pressure multiplied by area, which is AO. Pressure multiplied by AO is the extrusion force. We have extrusion ratio. We call it as Rx equal to AO divided by AF. AO divided by AF is the extrusion ratio. The true strain here, true strain, because you strain the material, right? You deform the material. As long as you deform the material, as you can see here, it means that you strain the material. So what is the strain? Definitely we talk about what? We talk about the true strain, not engineering strain. This is true strain. So true strain equal to ln AO divided by AF. AO divided by AF equal to ln, proportional to length also, LF divided by LO, which is ln Rx. This is Rx AO divided by AF, which is the extrusion ratio. So this is a true strain value. This is a true strain value, can be obtained in this way, right? In the extrusion process, it's very similar, like applying compression, like compressing the material. It's very similar to like compressing the material. When a pressure here, flow stress. This is the flow stress. This is the flow stress, right? Flow stress. Here, this is a flow stress, is like you're applying stress to flow the material. Then pressure here, actually, pressure applied here, equal to Y flow multiplied by epsilon X, Y average flow. Here, Y average flow multiplied by epsilon X, Y average or average flow stress multiplied by epsilon x. It's very similar to like applied compression. However, strain happening here in this area, which is epsilon x, right? This is a pressure in extrusion process equal to y bar flow average flow stress multiplied by epsilon x. Y bar flow equal to k epsilon n divided by n plus 1. Epsilon we can obtain as ln rx is a normal case. This is the ideal case. This is the ideal case, and no this is ideal case, ideal deformation, and no redundant work. Then epsilon can be obtained as a ln rx, and pressure equal to y bar flow ln rx. This is in perfect case or ideal case. But if you consider the non-homogeneous deformation case, then Johnson, which is a scholar working in this direction, Johnson introduced some modification to the equation, which is also pressure equal to y bar flow epsilon x. Epsilon x, this one epsilon x, he said that it is not simple like ln rx, but epsilon x, this one, in case of the extrusion, in case of non-homogeneous deformation, in case of here, then epsilon x equal to a plus b ln rx, a plus b ln rx. And he called this one is the extrusion strain. This one is the extrusion strain equal to a plus b ln rx. Ln rx is true strain. A and B are constant. Let me show you. Then A and B, then pressure equal to y bar flow multiplied by epsilon x, and epsilon x equal to A plus B ln Rx. Ln Rx. A and B are constant, equal to 0.8 and 1.2 to 1.5. It tends to increase with the increase of the die angle. Then it is from 1.2 to 1.5. It depends on the die angle. Usually is given in the problem. This one applied to indirect extrusion. So in case of indirect, listen to me carefully. I said in case of indirect extrusion, this equation is fine. Pressure equal to y bar flow multiplied by epsilon x. This is the pressure needed to flow the material. This is the pressure needed to flow the material. So pressure, the pressure, which pressure? Ram pressure equal to y bar flow multiplied by epsilon x, and epsilon x equal to A plus B ln Rx. Right? Then y bar flow here, y bar flow equal to K epsilon n divided by n plus 1, and the epsilon equal to ln Rx or ln AO divided by F, and so on. This one true in case of you talk about, this is the ideal case when you talk about the you talk about the indirect extrusion. But in case of direct extrusion, and somehow we have a little bit different. Why? Because in case of direct extrusion, ram apply pressure not only to deform the material, yes, to deflow the material, to deform the material, but also to overcome friction in the wall. There are a friction in the wall. It means that a pressure here applied, here to flow the material. This is the pressure, this is the part pressure needed to flow the material, which is equal to y bar flow epsilon x. Another pressure required to overcome friction in the wall, because when you push the material would like to move in this direction, again is, then there are a friction here, again is the motion. Then a pressure is not only y bar flow epsilon x, this is y bar flow epsilon x plus BF. BF, what is the BF? BF is the pressure needed. Then the total pressure equal to pressure to flow the material plus another pressure required to flow, to overcome the friction in the wall. Then this one, we know the value. It is exactly similar as we described earlier. This part we need to obtain what is the pressure, additional pressure to overcome the friction in the wall. This is the question actually. we can. Yes, عبد الملك. Yes, I'm
السلام
listening.
عليكم دكتور.
وعليكم
دكتور
السلام.
بخصوص الكويز أنا سلمت لكن ما أعرف إذا وصلك الPDF أو لا،
مش
وخايف
طيب
إنه
احنا
ما
بنص الكلاس. طب احنا
أنا
بنص
آسف.
الكلاس دلوقتي. طب اخلص الكلاس ونتكلم يعني، او تعالى لي في الاوفيس اور نتكلم يعني، عشان بس ما تقطعش
أنا آسف.
الدسكشن يعني. ماشي، لا ما يهمكش يعني. فايه لو ممكن تعالى في الاوفيس اور نتكلم. ماشي الكلام.
ما في مشكلة.
بس عشان ما نخرجش من المحاضرة وفاهم ما نعملش ديستربنس من المحاضرة يعني. ذات سيت يعني. تاني يا شباب يبقى البريشر here, pressure applied here is not only to flow the material but also to overcome friction in the wall. Then the pressure here, two part here, pressure to flow the material, which is the y bar flow multiplied by epsilon x. This one to flow the material, additional pressure required, which is the BF to overcome the friction in the wall, as I told you. Then the target is how to calculate this part. We need to know what is the BF value. What is the additional, the question, what is the additional pressure needed to overcome the friction in the wall, right? Okay, to do this one, I can tell you that whenever you apply pressure here, material would like to expand also laterally here in this direction. Then there are a pressure in the wall, we call it is the BC. BC, the pressure in the wall. The material need to expand. But the cylinder don't allow. Then the material apply pressure BC to the cylinder, right? BC, material apply pressure BC to the cylinder. This pressure distributed in the length here, right? Then you can see that this pressure multiplied by DL, which is the peripheral area, which is a by DL. If you multiply L is this one, this is L. If you multiply by DL here, then you get the force. Pressure multiplied by the area, you get the force applied to cylinder. If you multiply by mu, this is a normal force. Let me say, this is a normal force in this direction. Then I mean this pressure, if you multiply by the area, which is a by DL, then you get the force applied here and applied here. This force is a normal force. If you multiply by mu, you get the friction force. So friction force equal to mu multiplied by the normal force, mu n. So this is the n, so mu n. So friction force here, this is a friction force equal to mu n. This is the n, normal force. Normal force equal to B multiplied by dl, which is a circumstance area. So BC multiplied by dl is a normal force. You multiply by mu, then you get the friction force. So this is a friction force. Friction force then equal to the pressure multiplied by the area. This is the additional pressure, which is, because this is the additional pressure, the BF mainly to overcome this one. So then BF equal to BF, this force or this pressure needed to flow the material. We don't want to talk about this one. We talk only the additional one. Then additional pressure mainly to overcome this pressure multiplied by area give you the force to overcome the friction. Then pressure, which is the BF multiplied by the area, this area, which is a circle, by d square divided by 4, by d square divided by 4. Then the pressure here, BF multiplied by B square divided by 4 equal to the friction force. It must overcome the friction force, which is equal to mu n. Then you can see that this is the d square go with the do, right? By also here go with the by here. We can just clean this one. You can clean, right? There's some part here are similar. We can clean with each other, right? Then here it said that mu BC, this is the equation. BF by d square divided by 4 equal to mu BC by DOL. Mu BC here, he said that it is equal to YS, which is the shear yield stress and this ys equal to y bar flow divided by 2. So this value this value can be replaced by y bar flow divided by 2. And as I told you, this square go with this one, by go with by. I need to know what is the BF value. The question is, what is the BF value? Then from this equation, we can just simplify, clean it to get BF value can be obtained as, this is y bar, ys is y bar flow divided by 2, then y bar flow multiplied by, you clean, become multiplied by 2L divided by 2 TO. This is a part of pressure. This is a part of pressure required to overcome friction in the wall. Then go back to the previous equation, then the total pressure equal to pressure required to flow the material in the extrusion plus pressure to overcome the friction in the wall. So this one y bar epsilon y bar flow epsilon x plus BF. BF can be replaced by this one. Then you can see y bar flow can be taken as a common, multiplied by epsilon x, remaining here epsilon x here, 2L divided by the O. So this is the equation to just give you the pressure, or to obtain the pressure in case of use direct extrusion. Then we can conclude that we have two equations. One equation for direct extrusion, this is a direct extrusion. So this is the equation in case of direct extrusion. And the other one is the equation in case of indirect extrusion. What is the difference between the equation of direct extrusion and indirect extrusion? Direct extrusion here is exactly same indirect extrusion, but additional part we have here, which is to overcome the friction in the wall in case of direct extrusion. So this one y bar flow epsilon x, this also same y bar flow epsilon x. However, there are additional part here, which is y bar flow 2L divided by DO, which is to overcome the friction here. Then you can see that it is clear here that the pressure in case of indirect extrusion is lower than the pressure of direct extrusion. Yes, because this one have to apply pressure, additional pressure to overcome the pressure, the friction in the wall here. So you can see that this is the ram pressure. This is a stroke in case of, here you talk about here, this is the L. You see that material not flow, you increase the pressure. This is the indirect extrusion. Let me just highlight. This one is the indirect extrusion, and this one is the direct extrusion one. This is the ram pressure, right? This is the ram pressure. So whenever you increase the ram pressure, whenever you increase no flow, whenever you increase, when you reach to the flow stress, when you increase the pressure enough to flow the material will start to flow. In case of indirect extrusion, material flow at constant pressure here, you see that, until end. This is the end here, we reach to the dead zone. This is the dead zone area. We reach to this zone, we cannot deform anymore. In case of direct extrusion, here you increase the pressure, increase the pressure. You see that pressure here is higher. Pressure here is higher. And then when you reach to the pressure enough to flow the material and overcome the friction in the wall, material start to flow, and you can see that ram pressure decrease. Why ram pressure decrease? Because whenever you deform the material, L is getting smaller. When L is getting smaller, remaining L is getting smaller. When N is getting smaller, mean friction force is getting smaller. Then when friction force is getting smaller, then you can see that ram pressure will decrease. Theoretically, if L equal to 0, theoretically, if L equal to 0, it will never equal to 0, because it's still here, L will never equal to 0, because still here the dead zone will remain. But anyway, theoretically, if L equal to 0, then this one will be 0. Well, this one will be 0 means that it will be exactly equal to exactly y bar flow epsilon x, which is in case of you reach to the same value of the indirect extrusion. So this is the two equation, one of them for indirect extrusion, this one in case of direct extrusion. Then you need to know what is a process. If the process direct extrusion, then you use the first equation. If the process is indirect extrusion, you use the second equation. Right? This is the difference between case of direct and indirect extrusion. Right? If you need to get the force, force equal to pressure, whether it is direct or indirect. If direct, use the first equation of the pressure. If indirect, use the second equation. Then the pressure here, force equal to pressure, generally pressure multiplied by AO. This is the AO, because the pressure always applied to this one, not after but before. Pressure applied all time, pressure applied to the workpiece here, which is you extruding right here, not here. There are no pressure here. It's because it happened. I see some students say pressure multiplied by AF. No pressure on AF, pressure on AO, right? You understand me? So the force equal to pressure here multiplied by AO, and the power definitely equal to force multiplied by V, and V here is speed of the ram, Then force multiplied by V equal to the power of the extrusion process, right? Let's take an example. Let's read it and understand. A pellet 75 millimeters. This is a guy, This is a pellet that we're going to use in extrusion. We put this pellet for extrusion, right? Pellet 75 millimeter long, 75 millimeter length is 75 millimeter, and 25 millimeter in diameter. 25 millimeter in diameter is to be extruded. In a direct. In what? Direct extrusion. Very important. This one is direct extrusion operation. Then we use the direct extrusion equation. We'll use the direct extrusion equation, right? With extrusion ratio equal to 4. Extrusion ratio Rx equal to 4, right? Rx is extrusion ratio equal to 4, right? The extruded has round cross section. Yes, it is. The extruded has round. I mean, after you do the extrusion, the cross section here is also round cross section. Diangle is given, and the work material has a strength coefficient. This is K. Work material have strength coefficient, which is a K, and strain hardening exponent is N. This is the K and the N. Use Johnson formula with A and B. This is the constant. Johnson formula equation constant. A and B are given to estimate the extrusion strain. We need to know what is the extrusion strain. This is a question determined. This one, I mean A and B, these two constant is obtained to obtain the extrusion strain or Johnson strain. Determines the pressure applied to the end. Mean pressure applied at 75, at 50, at 25, at L equal to 0, at different L. L is 75, L is 50. When you do some extrusion, you get 50 remaining, then you apply at 50, and then 25, and 0. Theoretically, 0 means that you do extrusion, complete the extrusion, and all material is extruded. Okay, he said that calculate the pressure. Both the pressure equation. Actually, this is a pressure equation. Pressure equation said that Y bar flow. Why I said like this? This one is related to direct extrusion. This is a pressure equation indirect in case of direct extrusion. Why? Because he told me. This case is direct extrusion. So this is the equation. Y bar flow epsilon x plus 2L divided by. This is the equation. You need to obtain. We have L, we have DO. L and DO we have. We need to obtain epsilon x and Y bar flow. Then put the equation. This is a Y bar flow. This is the epsilon x. Then Y bar flow equal to K epsilon N divided by N plus 1. and the epsilon x equal to A plus B ln Rx. Ln Rx is a true strain, right? Ln Rx is a true strain, exactly equal to the true strain, right? In this case, epsilon we don't know. Here epsilon, and here we don't know epsilon. Then we need to obtain epsilon. Epsilon ln equal to ln Rx. We know Rx, then ln Rx, then you get epsilon. Then epsilon is obtained. Then epsilon x can be equal to A plus B epsilon x. Then you can epsilon. Then you can obtain epsilon x. And then y flow equal to K epsilon n divided by n plus 1. Epsilon is 1.3863. Then you apply here, then you can obtain y bar flow. Then we know y flow and epsilon x. Then go to the pressure. Pressure here, he said that calculate the pressure at different lengths. So pressure here equal to y flow already obtained, epsilon x already obtained, 2L divided by dO. dO is given, initial diameter is given, which is 25 millimeter. Then you can see all value are constant except L. So this value is constant here. This one is, we know, this y flow we know, this dO flow, only L is variable. L is variable because he said L equal to 50, 75, L equal to 75, L equal to 50, L equal to 25, and L equal to 0. Start first with the 75, so this is 75. Second is 50, third is 25. Then you can obtain the value, then you get the pressure. This is the pressure at 75 is 3,300 something. Here, a pressure at 50 is 2,500, is less. And then pressure at 25 equal to 1,000 something, then less. You can see that the high pressure here at the bigger L. So at the beginning, this is 75. So this is at 75 is here. So let me that this is the all length. We didn't do anything yet. So this is corresponding to 75, right? 75. And then he said that 75, 50. 50 mean here. 50 mean, sorry. 50 mean here. So this is a 50. Length is 50, right? And here 25. Length 50 mean remaining, huh? 75, this is a 75. Let me tell you, 75 mean total length is 75. 50 is mean remaining. Remaining is 50. 25 mean remaining is 25. Because every time you do what? Every time you do pressure, the length, remaining length will be reduced. Initially, you start with 75. And then remaining length decrease to 50. And then remaining length is decreased to 25. So this is the three cases that we described. So 75 is the total length, 50 is remaining 50, 25 remaining 5. So you see that a force is decreased. You start here because here this is the highest friction, because the highest contact length, highest friction because highest contact length. And then when length decrease, getting smaller, a friction part here is getting smaller, then force is getting smaller. What about zero? What about zero? Still L equal to 0. If you apply L equal to 0, means this part will eliminate it. L equal to 0 means this part becomes 0. Then equation equal to B equal to Y bar flow epsilon X. Y bar flow epsilon X is exactly equal to the value, theoretically will be exactly equal to the value of indirect extrusion, which is a Y flow. This part, no friction because L is finished, so no friction. So that is exactly what happening here. In case of L equal to 0, this is L equal to 0. L equal to 0, this part is gone. Then the remaining Y bar flow epsilon X. This part Y bar flow epsilon X exactly is a case of, very similar to the case of indirect extrusion. Right? That's it. So next, shape of extrusion die orifice. Shape of extrusion die orifice. All whatever analysis we did previously, only and only for simple shape, which is a circular shape. So all analysis we did previously and the equations that we described here in the extrusion earlier, exactly for round cross section, only and only round solid round cross section, as you can see here. However, if the die here, this is the die here, have a more complicated shape, as you can see, not round, I mean chain different from now round and become complicated shape, as you can see here and here, then equation must be modified. Then equation or the equations that we described earlier must be discussed. So the equations that we described earlier for only circular shape, as you can see, circular extrusion, circular cross section. But whenever it is different from circular cross section, as you can see, to be more complicated, then this equation or the equation described earlier must be modified. This is the two equations that we show earlier. For circular shape, this is the first equation in case of direct extrusion. This is the second equation in case of indirect extrusion. Here the modification is this part. Modification we added, it is exactly same. However, we added whatever we call kx to the equation. We added kx to the equation. So in case of indirect extrusion, the pressure equal to y bar flow epsilon x. We added kx, then become kx y bar flow epsilon x. In case of direct extrusion, equation was y bar flow epsilon x plus 2L divided by TO. We added kx. Then new equation become pressure equal to kx multiplied by y bar flow epsilon x plus 2L divided by dO. Then only kx is added to modify the equation to adapt with the complicated shape produced in the die opening, to have this kind of complicated shape in the die opening. Kx, we call it is the shape factor. Kx here we call it is the die shape factor. Kx die shape factor. Kx here that we added, we call it is the die shape factor. So kx that we added, we call it is the die shape factor. Right, in extrusion. This kx equal to what? Kx equal to 0.98 plus 0.02 cx divided by cc power 2.25. This equation obtained experimentally. This equation obtained experimentally. You will ask me what is the cx and what is the cc. Listen to me carefully to explain to you what is the cx and what is the cc. cx is the perimeter of the extruded part. perimeter يعني بالعربي يا شباب المحيط. perimeter of the extruded part. extruded part يعني الجزء اللي احنا بنعمل له extrusion. perimeter of the extruded part. cc is the perimeter of the circle that have same area of the extruded part, or same area with the extruded part. Let us take an example and see how to calculate and then explain why exactly area. Area is circle. Right. This is a shape, different shape. This is a different extruded part. I mean, this is the extrude. Initially, it is cylinder. Before extrusion, the part is cylindrical shape all time. Later, it is extruded this kind of complicated shape. So this is the extruded part. Extruded means after extrusion, means the part when exit from the opening die after extrusion. So after extrusion this is the first example. This is the second example. This is the third example. This is the fourth example. This is we have here 4 examples as you can see. This is a rectangular shape. This is the hollow cylindrical shape or circular shape. This is, as you can see here, different shape, right? We need to obtain shape factor for each case. kx in each case. kx equal to what يا شباب؟ equal to 0.98 plus 0.02 cx plus cc power 2.25. Start first with this one. First case is this guy. This is the extruded part, right? This is the first case. Start A with the first case. This is the extruded part. This is the extruded part. We need to obtain shape factor. What is the shape factor of this kx? Okay, equal to, we need to obtain cc and cx. If we obtain cc and cx, we can understand what is the k, or calculate what's the kx. First, what is the cx? Cx, listen to me carefully, guys. Cx is the perimeter of the extruded part. This is the extruded part. Perimeter is المحيط بتاع الشكل ده. اللي هو ايه المحيط يا شباب؟ ده 20 وده 60، يبقى المحيط عباره عن 20 زائد 60 زائد 20 زائد 60. 20 plus 60 plus 20 plus 60. Then the perimeter of this guy equal to 20 plus 60 multiplied by 2. This is the cx. So cx is perimeter of the extruded part. Then cx finished. What is the cc? Listen to me carefully. cc is the perimeter also. المحيط برضه. يعني cx محيط والcc محيط. cx محيط الجزء ده. خلينا اعمل له هايلايت. الcx مباشرة محيط سوري. الcx يا شباب محيط الجزء ده على طول مباشرة. الcx هي محيط الاكسترودد بارت مباشرة. ماشي الكلام؟ الcc بقى محيط ايه؟ محيط دايرة. الcc دي محيط دايرة. دايرة ايه؟ الدايرة دي cc محيط دايرة. الدايرة دي have same area with the extruded part. يعني الاريا دي equal to الاريا بتاعت الدايرة والcc محيط الدايرة دي. طب نعمل ازاي؟ First we obtain the area of the extruded part. The area of this guy equal to 20 multiplied by 6. This is the ax. This is the ax. Ax equal to 20 multiplied by 60. This is the area. This area equivalent to the area of imaginary circle. This circle is not exist imaginary. احنا بنتخيل وجود دايرة. الدايرة دي تخيلية imaginary. Then ax equal to AO, right? Then AO equal to what? By r square. AO equal by r square. Then by r square equal to 1200. Then r equal to, this is the radius. Then what is the perimeter? Perimeter equal to cc. 2 by r, which is we obtained here. Then you can obtain the perimeter cc. Imaginary circle. Someone will ask me why we do this. Actually, we said that, please listen to me carefully. We said that all calculation, the previous analysis we did for circular extruded bar. Circular extruded bar. That's why we do comparison actually between the circular shape, that which is the default shape, and the exact or correct or actual shape. So this is comparison between the actual shape and the circular, which is the default shape. So this is the actual shape, and we here converting the actual shape to circular shape and make a comparison. We can obtain the shape factor. Do you get it? This is the idea. So this is the idea. So the area, so again, this is the perimeter of the guy, directly perimeter of the guy. This is the perimeter also. But what? Default shape, which is a circular shape, which is not exist. So we converting whatever we have to the circular shape. Get this area and equivalent areas, then you get the radius, and when you get the radius, you get the perimeter. So this is a perimeter. Perimeter divided by perimeter. Then kx equal to 0.98 plus 0.02 plus Cx divided by Cc power 2.25, then you get the Kx, which is a shape factor in the first case. Okay, shape factor in the second case. Shape factor in the second case. Okay, immediately. First, we need to obtain what is a Cx, what is a Cc. Cx, yeah, directly of this guy. Cx is the perimeter, directly perimeter of this guy. Perimeter of this guy is what? Is two perimeter. Outer perimeter, this one here, perimeter here, is the outer perimeter and the inner perimeter. This is the total perimeter. Cx here is the total perimeter. Somebody said this is a circular shape. It is hollow shape. When we talk about solid circular, the default one is a solid circular. This one is hollow. Hollow means it is not same. It's different. Then we have to apply only circular shape. We not apply for solid circular shape. Then a perimeter here is a two perimeter. Is a by DO is a one perimeter, and by DI is a second perimeter. So one outer perimeter and inner perimeter. So perimeter Cx is a total perimeter. C by DO and by DI. Then D outer is 50, D inner is 45, because here 2.5 and 2.5. Then the inner diameter is 45. Then you get the Cx. This is Cx. What is the Cc? Cc, you need to get the area. You need to get the area of this guy and make it area of the circle and get the radius and get the perimeter. What is the area of the ring? Area of the ring. We need to obtain the area of the ring here. We need to obtain the area of the ring, right? Area of the ring Ax equal to what? Is a by RO square minus by R inner square, which is a by R outer square minus R inner square, because you need to obtain the area of the ring, which is the bigger area minus the hollow area. This is the Ax. Then Ax obtain, then Ax equal to the area of this guy, then R square. You get the radius of solid one, then you get the Cc 2 by R, then you get the Cc, then you can obtain Kx, as you can see, apply an equation. We need to obtain these two guys also. This is another two examples. Let's just move forward. C is this one. We need to obtain Cx and Cc. Cx directly, as I told you, Cx is the perimeter of this guy. Directly a perimeter of this guy. What is the perimeter of this guy? Perimeter of this guy mean المحيط يعني بتاعه يا شباب. يعني اللي هو ايه 30 plus 60 plus 30 plus 5 plus 25 plus 50 plus 25 plus 5. The 30 plus 60 plus 30 plus 5 plus 25 plus 50 plus 25 plus 5. محيط يعني مجموع كل الأطوال اللي موجودة عندنا دي. المحيط بتاع الجزء ده. This is the Cx. I think easy, right? Cc, what is the Cc? Cc, you need to obtain the area of this guy, which is Ax. You can divide, actually. You can divide. I mean, you can just make, you can cut here. You can to make it like easy engineering shape. You can make cut here. Sorry. This is the one rectangular, and another rectangular. There's three rectangular, for example. You get the area. Then area is this one and this one similar, same size. Means 30. This not 30, 25. 25 multiplied by 5. Then 25 multiplied by 5. This one is, yeah, it depends on how you divide. Maybe you divide this one, make it 30 multiplied by 5. You can cut here, you make it 35 and 35. Here he cut, it seemed like cut like this. 30, yeah, make 35. Then total here, this is 30 multiplied by 5, this is 30 multiplied by 5, 230 multiplied by 5, plus 5 multiplied by 50, this is a 50. 60 multiplied by 10, meaning 50. Then you get the area. This is the area of this guy. The area of guy equal to area of cylinder. Then you get the radius and you get this one. Then you get a Kx. Okay, for this one, how to obtain? You need also obtain the perimeter. In same way, actually. Perimeter equal to, you need to calculate all lengths to get the perimeter and get all area to cut, get all area, and then they get the radius and calculate. It is very simple, and then this is answer solution is here, right? This way you get shape factor. If you get shape factor, you can apply equation, then you get the pressure. Then the pressure, you can either use the direct extrusion or indirect extrusion, which is equal to kx multiplied by the, you can just simply add kx to the equation, then you can obtain the pressure value. Let's take this example and stop, right? This is a nice example. Let's read together and understand and try to solve together. A cup-shaped part, this is a cup-shaped part, is produced. Do you remember? This is a cold extrusion that we described earlier. Yeah, this is a piston and this is a workpiece. You put here, you apply pressure, material will flow to create with this whatever we call cup shape. This is a cup shape. Cup يعني كوباية. Cup shape part is backdraw extrusion. This is the in. Listen to me carefully, guys. This is a backdraw here. This is a backward extrusion. Backward extrusion, which is the indirect extrusion. You see why? Because material flow in opposite direction. You apply pressure here, then you apply pressure in this direction. Material flow in opposite direction. So this is the indirect, indirect extrusion, not direct. This is the backward extrusion from aluminium slug. This aluminium slug, initial work with aluminium slug, 50 millimeter in diameter. This material is 50 millimeter aluminium slug, 50 millimeter in diameter. This one, inside diameter 40 millimeter. It is made of aluminum. This one 50 millimeter. Inside diameter, so outside diameter 50 millimeter, inside diameter, the cup one. So cup one outside diameter 50 millimeter, it will exactly same. Outside diameter is same. Inside diameter is 40 millimeter. Right. So this here you can from up you can see it is ring shape. Right. It is ring shape. It is 50 millimeter. This one 50 millimeter diameter. Inside is 40 millimeter diameter. Height millimeter. Height is 100 millimeter. Height here is 100 millimeter. Right. And thick base 5 millimeter. Thick base remaining because here you see that it is like this. This is a base, remaining base here. Remaining base. The thickness of the base is 5 millimeter. Thickness of the base here. It is not open from up and down. It is open from up, and there are a base here. The thickness of the base remaining is 5 millimeter. Determine extrusion ratio. We need Rx. Rx obtained as AO divided by AF. Where is the AO? AO is here. This is the AO, initial area, right? Where is the AF? This is the AF, final area. AO equal to what? Equal to by divided by 4. This is a by divided by 4, 50 square, which is the DO diameter. AF equal to what? AF equal to, this is the final area. This is the final area, right? Equal to what? Final area equal to by divided by 4, 50 square minus 40 square. 50 square minus 40 square. This is the AF. Then Rx, obtain Rx. This is the first question. Second question, what is the shape factor? What is the shape factor? This one we had example very similar to this one. Do you remember? So this is the example. So shape factor. So shape factor is very similar to the example that we had just in a previous slide. Then you need to get Cx and Cc. Cx equal to what? Directly the perimeter of this guy. Perimeter of this guy, 2 perimeter, outer perimeter and inner perimeter. So by 50 plus 40. This is the outer perimeter. This is the inner perimeter. This is the Cx. So Cx can be obtained. Then you need to obtain Ax, which is the area of the guy. Area of the guy here, which is final, is 706.86. This is the area of this one. Then you get this one, the area of this one, equal to by r squared. Then you get r. R radius of imaginary circle or default circle. And then you get a Cc, which is a perimeter, by 2 by r, which is 15. Then you get Kx equal to, you put the equation, then you apply Cc and Cx, then you apply, you get the Kx. So second one is a shape factor. Third one, we need to know what is the height of starting slug. We need to know what is this height. Starting slug. What is the height of starting slug? This is a question. What is the height of starting slug? Actually, volume is constant. Volume is constant. You start with certain volume, you end with the same volume. So this volume must equal to this volume, right? So we need to know the diameter is 50. We need to know the height of a starting slug. Let me go to the next slide. So this is the one you obtain actually. You start with this one, you get this one. This one we can divide to 2. Because this is a base, right? This is a base. We can divide to 2. We need to get the volume of this guy. Because the volume of this guy equal to the volume of the starting material. So this one divided to ring, we cut here. Why we cut? To make it simple, area. So it simply can be calculated. So this is the base and this is the hollow ring, right? The base here, he told me it's 5 millimeter. He told me it is 5 millimeter. This 5 millimeter. Then this one 95 because 100 is total. This one 5, this one 95. Bigger diameter, this one is 50. This one is 50 millimeter diameter. Outer diameter is 50 millimeter. Inner diameter is 40 millimeter. We need to obtain the total volume of this guy. We need to obtain the total volume of this guy, right? Total volume of this guy, which is this one plus this one. Total volume of this guy equal to the volume of this one plus the volume of this one. This total volume equal to the volume of a starting slug, which is half diameter 50 millimeter, and we don't know the height. Then we can obtain the height. This is the idea. This is the base. This is the volume of the base. This is the first here. This is the volume of the base. This is a base. Right? This is the volume of the base. Base equal to 5 millimeter here and diameter 50 millimeters. This is the volume of the base. This is the outer. This is the ring, hollow ring. This is the diameter of the hollow ring. Outer diameter 50, inner diameter 40, and the height here is 95. Then you get the volume. This is the volume of the ring. So this is the volume of the ring. Then total volume, you can obtain total volume, which is the volume of the ring, and total of the base. This is volume, total volume. This total volume equal to the volume of this guy. So it is same with the volume of this guy. Because the volume is constant, you agree with me? Then this guy, we know diameter is 50, then we need to know the height, then you can obtain the height. Height can be obtained. This is the third one. Force, we need to know what is the pressure and what is the force. The last equation, D, what is the force applied? D is what is the force applied. Put the equation of the force. Force equal to pressure multiplied by AO. Pressure multiplied by AO. Right, pressure here, this is direct or indirect. The question is to know the pressure. Pressure, this is direct or indirect? This is indirect. How you know? Because the pressure is applied in this direction and the material flow in opposite directions. This is indirect. This is the pressure in case of indirect extrusion equal to Kx, Y bar flow, epsilon A. This is a pressure equation. This is the pressure equation in case of indirect extrusion. Then equal to Kx Y flow multiplied by epsilon A. Kx already we obtained in the last slide. So we know Kx. We need to obtain Y bar flow. We need to obtain epsilon X. Y bar flow equal to K epsilon N divided by N plus 1, and the epsilon X equal to A plus B ln Rx. Rx we already obtained in the first slide. In the last slide, I mean, epsilon equal to ln Rx. Epsilon to ln Rx. Rx is the first, which is question number A. Then epsilon here ln Rx. Then get epsilon. Epsilon X equal to A plus B ln Rx. Epsilon X is obtained. Y bar flow equal to K epsilon N divided by N plus 1. K and N given, and epsilon already obtained and ln Rx here. Then you can obtain Y bar flow. Then Y bar flow obtained. Pressure equal to Kx Y bar flow epsilon X. Then you can apply, you get the pressure. This is the pressure. We need to obtain the force. Force equal to pressure multiplied by EO. Listen to me carefully, guys. Force equal to pressure. Pressure is already here. This is the pressure multiplied by AO. Where is the AO? AO is the area that the piston applied. Listen carefully, guys. Area that AO is the area that the piston here. This is the piston applied. What is the area here? The area here is 40 millimeter because the piston apply inside. Then the area here diameter is not 50 millimeter. This 50 millimeter, I agree with you. This guy is 50 millimeter, but the piston is only 40 millimeter. Material will flow in a gap between the piston and this. So diameter is 50 millimeter, but piston diameter is 40 millimeter. Then the pressure applied on 40 millimeter. Then the area here, AO, is corresponding to 40 millimeter. Then area by divided by 4, 40 millimeter square. This is the area of the pressure, AO. Then force equal to pressure multiplied by AO. Power also can be obtained as force multiplied by the V of the ram, speed of the ram. Then power can be obtained. I hope it is clear, and if any one of you have any question, can come to me in office hour. We can come discuss in detail if there are any question. Tamimi, yes, I'm listening.
دكتور ما قاطعك، خلصت انت شرح لان عندي بس شيء بقوله.
خلصت خلاص يعني almost done. I'm going to finish now. فاضل 2-3 slide. If you would like to go, you can just go, no problem. But clear, any question? Do you have any question before you go?
لا
Is it okay? Is it clear?
ايه
clear واضح بالنسبة لك؟ عندك أي سؤال؟ أي استفسار؟
عندي بس في الكويز صارت لي مشكلة بسيطة، بس ودي
بس عشان اكمل المحاضره، يعني انا قصدي سؤال في المحاضره. لو عندك سؤال في الكويز يعني تعالى لي في الاوفيس اور، يو ار فيري ويلكم. بس عشان اخلص المحاضره، انا خلاص فاضل لي 2 أو 3 سلايد هخلصهم واخلص المحاضره، وبعدين نتناقش ان شاء الله. لو تعالى في الاوفيس اور نتكلم يعني.
متى الاوفيس اور اليوم؟
الساعه 1:30 ان شاء الله لغايه 3.
ما يمدي دكتور بعد السلايدات بعد ما نخلص يعني بس
خليك معايا ونخلص واسالني، مفيش مشكله. خلينا اكمل بس خلينا اكمل الكام سلايد الفاضلين يعني.
ايه معليش
لا خالص مفيش مشكله. This is the extrusion. So this is almost finished. So this is the extrusion process. Extrusion process usually hydraulic or mechanical. There are a mechanical way which is used in cold extrusion and mechanical drive or hydraulic drive in different cases for extrusion process. Die angle also affecting extrusions. So die angle could be have big die angle, small die angle. So in case of big die angle and small die angle, extrusion force will increase and decrease. Not there are certain value in the middle to get the optimum case. There are a certain value optimum or certain value not small, not big, but something in between. So optimum angle usually something in between, not very small angle, not very big angle, but something in between. This is the optimum angle in the extrusion process. Definitely temperature affecting the extrusion pressure. Whenever the temperature increase, extrusion pressure decrease. This is a temperature, increasing temperature. Whenever this is a higher temperature, lower, this is the room temperature, or cold working, this is a cold working, higher temperature. Whenever temperature increase, you can see the pressure usually decrease, the extrusion pressure usually decrease, because you know that material becomes softer and then easy can do. This is almost the end of the chapter here. The effect of the extrusion, we have whatever we call surface crack, and we have whatever we call is a piping. Surface crack is a crack initiated in the surface here, and mainly friction. High speed extrusion and the friction and the strain is high, and the high speed you do extrusion at a high speed, and the friction increase, then tearing happen and the crack happen initiated on the surface. Another one we call it is a piping or tail or fish tail. We call it pipe or tail pipe or fishing or tail fish tail, which is material like this. This is one inhomogeneous deformation. Extrusions, the surface oxide and impurity tend to draw inside, and impurity يعني الماتيريال الفورم material become in the middle, become weak, and then become like, as you can see, we call is a piping or tail. Then it is simply you can solve this one by using material without, I mean, any kind of contamination. So must be material to use for extrusion, must be as a pure material. And also here the dead zone also increased based on the friction as we described earlier. Next is whatever we call is a center brush. Center brush is also something like this one. This is the actual photo of center brush. It could be below the surface or on the surface, like crack on the surface like this. Also, this one promoted by high die angle, low extrusion ratio, and impurity also promoting this one. Indirect, internal, it could be internal and could be also external. This is the type of defect could happen in extrusion process. This is the end of the extrusion, and next part will be wire and bar drawing. I will stop recording.